Discrete random variables, page 5. When rifle shooter Hui fires a shot, he hits the target 80% of the time. If Hui fires 4 shots at the target, determine the probability that he has 2 hits and 2 misses in any order, at least 2 hits. Okay, so remember, 4 tries corresponds to 14641, Pascal's triangle coefficient, row, and 80% chance of success, so that would be 0.8, 0.8, 0.8, 0.8, and then chance of failure is 0.2, of course, because it's, 1 minus 0.8 is 0.2. 0 failures, 1 failure, 2 failures, 3 failures, and 4 failures. 2 hits and 2 misses in any order corresponds to this term here. 2 successes, 0.8 squared. 2 misses, 0.2 squared. 6 ways of that happening. Pascal's triangle coefficient 6. So that would be, let's just do that in the calculator. 0.8 squared. It's going to be 0.64. 0.8 squared times 0.2 squared times 6. 0.1536. At least 2 hits. At least 2 hits would be these 3 terms, right? So the first term is 0.8 to the 4th. .4096. And then 3 hits would be 4 times 0.8 cubed times 0.2 to the first. 0.4096 also. So if I want the probability of at least 2 hits, I would add these 3 together, because it would be 4 hits, 3 hits, and 2 hits all added together. So I have 4096 twice, and I add that to 0.1536. .9728. Okay, there must be a better way than to do this. I mean, it's just this pattern here. Can't they computerize it? Yes, they did. The way they computerized it is they gave you 2 choices. One is they have binomial PDF. What does binomial PDF do? Binomial PDF, what it does is it picks out one of these terms. So if you want one of these terms, it'll do it for you. All you need to do is tell it the basic information like 4 shots, 0.8, and you desire 2 hits. If you give it those 3 pieces of information, it can figure out what the value is, 0.1536 of one of these. Okay? Let me show you how to do that. So you just do second distribution. Where is it? Binomial PDF. And we'll talk about what CDF would mean later. 4 tries, 0.8 chance of success. How many times? X means successes, so it would be 2. Paste. 0.1536. 0.1536. See? Works. Okay, what does binomial CDF do? So binomial CDF does this case where it says like at least 2 hits. Okay, but binomial CDF is a little bit different. Instead of doing at least 2 hits, it always does 2 or less, 3 or less, 1 or less. So it doesn't do at least, which is like more. It does kind of the opposite. It does like 2 or less. Okay, so it'll do these 3 down here, for example. So if I do binomial CDF, second distribution. So I think that what I'm going to do is, I'll use binomial CDF And this is the way you're actually going to do it in real life, so it's kind of useful. So what you're going to do is you're going to use binomial CDF to calculate the opposite of 0.9728. You're going to do these two. And then you're going to subtract it from 1, and that'll give you 0.9728. Okay? So I'm going to go down to binomial CDF, and I'm going to give it the number of trials of 4, and I'm going to give it the success rate of 0.8. And then I'm going to give it the number of successes. And in this case, I'm not going to put 2, because that would be this. I want to put this. I want to put the pink part, or less. So number of successes, just 1, right? There's 1 success here. And then I do paste. And then this is going to give me the probability of these 2 happening. And then if I want to find the probability of these 3 happening, I would just do 1 minus this probability, which gives me 0.9728. Okay, so remember in inverse norm, if you have the old calculator, you have to do that thing where you you always think the distribution is going to be the left side. Same thing with binomial CDF. Binomial CDF only does left side distributions. Okay, if I was to draw this in a picture, what I have is I have like kind of like normal distribution, except for binomial distributions are like, they look like histograms, they're like square. And like, let's say that I want the case where I have 2 or more successes. So 2, 3, 4 successes. And here I have 0, 1. Notice that if I want this part, which is 0.9728, the way I would do that is I would tell the calculator that I want this part, and then I would subtract it from 100%. Okay? So I would tell the calculator, I'd say, okay, I want 1 or less successes, and that the calculator would give me this part, which turned out to be 0.0272. And then I would do 1 minus 0.0272. Okay, now that we saw how to do it, I'll show you this calculator procedure, which is a little bit hard to understand, I think. Unfortunately, this calculator procedure is written for an older version of the calculator that doesn't give you the screen, which allows you to fill in everything by prompts. So the probability that x is equal, the probability that random variable x is equal to r is equal to remember that? Where P is the probability of success, N independent trials, R successes, and N minus R failures. Okay? Look familiar? This notation here, we've seen this before with normal distribution, except for a normal distribution, of course, it was capital N. This basically is a compact mathematical way of saying random variable x is distributed in a binomial distribution with N trials and P success rate. Okay, so the random variable x is distributed as a binomial experiment with parameters N and P. Okay, for which of these probability experiments does the binomial distribution apply? Justify your answers using a full sentence. A coin is thrown 100 times. The variable is the number of heads. Let's talk about the conditions we need to be able to use binomial distribution. One of the things is that we have experiments with 2 outcomes, right? So we have some experiment with 2 outcomes, and even if you have something that's like 6 outcomes, like a dice roll, you could make it into 2 outcomes by saying 6 or not a 6. Okay, so we've taken a 6 outcome thing and make it into 2 outcomes. So we need an experiment with 2 outcomes. Each trial of the experiment needs to be independent from the other. Okay, so independence. And the probability of each one happening has to be the same. So it's like repeated with the same p-value or probability of success. You know, like when you have with replacement, without replacement? Well, without replacement violates 2 things. one, it's not independent, right? So like if you have without replacement, then the first experiment affects the second experiment. The other thing is they don't have the same p-value every time, right? So that's kind of what we're looking out for. We're looking out for, is there a without replacement condition here. A coin is tossed 100 times. The variable is the number of heads. Coins, you're already eliminating the possibility of not replacing, right? So yeah, it's like in this case you have 100 trials. The coin has a probability of 1/2 every time. It's always the same. It's independent. You could write all those things in a sentence or several sentences. 100 coins are each thrown once. The variable is the number of heads. So yeah, this is also fine, right? It's flipping 100 different coins at the same time is the same thing as taking one coin and flipping it 100 times. A box containing 5 blue and 3 red marbles. I draw out 5 marbles, replacing the marble each time. Oh, that's the key word. I'm replacing. So since I'm replacing, it is possible to treat this as a binomial distribution experiment. The variable is the number of red marbles drawn. So you could draw attention to that, right? That, oh, I'm replacing the marble every time. The number of trials is 5. The p-value is always the same because I'm replacing every time. So how could I ruin this last one? I could say I don't replace it each time. I draw out 5 marbles and I don't replace each time, right? Then it's not independent anymore. The p-value changes. I could also ruin it by saying I draw out 5 marbles all at the same time. Okay, how is that different than B? If I draw 5 marbles out at the same time, then it is as if I drew out the first marble and didn't put it back and then drew out the second marble, right? Because like the 5 marbles that I draw out, they can't all be the same marble, right? So it's not the same as drawing 5 marbles out one after the other and replacing them each time. Okay? And that's it for today.